Today, I am going to talk about a recent result about Betti numbers of unordered configuration spaces of a punctured torus. This is a joint work with Cheong. We set out the notation. The ordered configuration space fxn is an open subset of a Cartesian product x to the power n, such that no two coordinates are the same. And the unordered one is the topological quotient by the symmetric group Sn, where the action is permuting coordinates. They are important objects in the study of topology, and many authors have used various invariants, including homotopy groups and singular cohomology groups, to give information about their topology. And today we ask if we can get all the singular Betti numbers in rational coefficients of all the configuration spaces of a fixed space X. And for the purpose of today, we only consider the topological space X that comes from a smooth complex variety, as they will behave nicer and have a richer structure for the study, even though the question itself only needs the topology of X. And let's visualize a little bit about what the configuration spaces look like. Well, conf 0 is just a point, and conf 1 is the space itself. And when n is at least 2, the quotient here will make it harder to visualize, so it's helpful to consider a symmetric product. Here we define sim nx to be the Cartesian xn quotient by the symmetric group also permuting coordinates. And you can view them as the set of multi-sets with n elements in X, where the order doesn't matter, but repetition is allowed. So conf n will be an open subspace of sim n, whose complements are a set of multisets with at least some repeated elements, and we call that big diagonals. When X is C, this will give a special case where we have good visualization because we have sim n C is isomorphic to C to power n via, well, fundamental theorem of algebra, because here the map is basically you will go from the set of roots of a polynomial to the coefficients of a polynomial, and they are given by the elementary symmetric polynomial. And using this identification, we can move everything from sim n to C to power n, so we can view conf nc as an open subset of Cn. And we only need to figure out what the complement is. When n is 2, the complement is the parabola. So conf 2c is C2 minus the parabola, but that is isomorphic to C2 minus x-axis. And that is homotopy equivalent to a circle, so the Betti numbers are known, and every topological information is known about that. But for n at least 3, the topology is already quite interesting, because the complement that we take out will be called the discriminant hypersurface, which is the set of all the E1 to En such that this polynomial has discriminant 0, meaning having repeated roots. Even if n is 3, the complement is already interesting. In fact, it's a homotopy equivalent to a trefoil knot. However, even though it is already hard to visualize x equal to c case when n is at least 3, but the Betti numbers are well known and has a simple answer. And this is a classical theorem of Arnold, saying that all the conf nx only has S0 and H0 and H1, and the H1 only starts to appear beginning from n equals to 2. And in fact, when X is C with multiple punctures, we also understand the configuration space well. This result is not written anywhere, but we can easily derive them from a combination of two results, and we will show that later in this talk. So what it says is that this number, in terms of I and n, can be given coherently via one single generating function in two variables. And the generating function is a rational function. And how about more cases? Well, for the previous case, we can summarize them by the genus, because you can see that if C if x is c minus some points, you can view them as the genus zero curve, which is P1, the Riemann sphere, minus a certain number of points. And we can ask what happened for other general curve, any genus punctured with any number of points. So if it's genus zero case with no puncture, then there is also a result about the Betti numbers of configuration space. And in fact, there are explicit formulas whenever x is a smooth projective algebraic curve with certain genus, with certain punctures. And the explicit formula will be in terms of binomial coefficients and many case-by-case things there. And now the problem is that there is no readable and comprehensible pattern has been discovered, as the orders admit. So our goal here is to find some nice generating functions that hopes to summarize these numbers in a nicer way. And here is our contribution. In the case where x is an elliptic curve minus a point, then we have a rational generating function, except that the power here is not quite just u to power I, but some weird thing. And this thing can be given in the table, and this is the real novelty here, precisely because we need this weight pattern here. And so, and this is, then it will be imaginable that if we try to extract the coefficients directly from the generating function, you will get some very complicated combinatorial formula. And also note that since the weight is decreasing, this theorem alone can recover all the relevant numbers here. And we remark that we don't need the structure of elliptic curve, not the complex variety structure, and also not the group structure. We just need, because this question itself is totally topological. But it turns out that we will need to, in the proof of this result, we will need to identify E as a complex manifold, as a complex variety, in order to use some more tools there. And to see how the main result works, we can use this table. Basically, what it says is that if you expand these rational functions, then you can read the coefficient and get all and get the tables of Betti numbers. And the only strange thing is that you always skip some of the powers. And now we're going to focus on the proof. And there are three main ingredients, and we're going to talk about them when we get there. The first ingredient is cut and paste. We know configuration spaces in terms of how they are made up of simpler varieties. So by making up of simpler varieties, we mean that we decompose them into locally closed subvariety via this way. An open one plus a closed one, we say that it is equal to the whole space. And we use the bracket to denote it. So here the abelian group K0 var C is called a Grothendieck ring. And this is precisely the place to encode the cut and paste data. And the knowledge about configuration space is the following, is that there is a nice generating function that tells us how to build up configuration spaces from the symmetric products. So for example, at degree 2, this formula simply says that conf2x is sim2x minus x. But we already knew that because conf2x is sim2x minus the diagonal, which is isomorphic to x. So the upshot of it is that we can build up the configuration spaces from symmetric products, whose cohomology is already well studied, starting from a result of MacDonald. But there is a problem. We care about Betti numbers, but they don't interact well with cut and paste. In other words, if you have a cut and paste like this, where U is open in X and Z is the closed complement. We don't necessarily have that the Betti numbers add up. So we need some finer structure in order to harvest this combinatorial knowledge. And this harder structure is the mixed Hodge theory. And this is also the reason why we need to consider complex varieties, even though the original question doesn't need the variety structure, only the topology. So recall the classical Hodge decomposition that works for smooth and projective complex variety, or Kähler manifold. We can decompose the singular cohomology in terms of HPQ, but there's a constraint that P plus Q must be the degree I here. And Deligne develops a mixed Hodge theory, which is a generalization of this, but works for all complex varieties, including the non-smooth one and the non-projective ones. They can give vector space HPQI, and we can sort of view them as a decomposition of HI, the singular cohomology, except that the inner structure is more complicated than that, and there are some filtrations there. But for our purpose today, all we need to know is that at least the dimensions can be thought of as a decomposition, in the sense that this dimension adds up, and we know that we no longer have the constraint P plus Q equals to I. So we are really decomposing HI in terms of this for all possible choices of P and Q. And we also say a special feature of the smooth projective varieties, which is called purity. So if P plus Q always equal to a certain number, then we say that you have purity. So in this terminology, for smooth projective case, HI is pure of weight I for all I. And here, as a terminology, the term weight always means P plus Q. Okay. So although we don't need to know anything here, but let's give some more intuition of how the mixed Hodge theory works. Roughly speaking, the part of HI with correct weight, which is I, remembers the Hodge structure of some smooth projective variety associated to X. And the part with higher weight is contributed by how far X is from being compact. And the part of lower weight comes from the fact that X is not smooth. So they basically remember certain data about the difference between X to a smooth projective version of X. And as a toy model example to illustrate this, and let's say X is X bar minus D, where X bar is smooth projective and D is a divisor, a smooth divisor. Okay, then HI has only parts of weight I and I plus 1, and the weight I part records the smooth projective version of X, which is X bar. And the weight I plus 1 part is a contribution of the complement D, so that is how far X is from being compact. And note that X bar and D has both Hodge decomposition in a classical sense, and that's how the mixed Hodge theory of X is roughly built. So we don't need anything here. We just need to know that HPQI is a black box decomposition of HI that satisfies one more property that we need. Next slide. So the next property we need is that whenever we have purity, then we can get a nice information that you can make use of the cut and paste knowledge. So this is the important fact we need today, is that if HI has purity of weight Wi, then the left-hand side polynomial here, it is something you can compute once you get the cut and paste data of X. Right? And notice the power here is 2n minus Wi. And the real reason behind is that this alternating sum in terms of I is determined by the class of X in a quadratic ring. This can be viewed as a mixed Hodge version of Euler characteristic. And actually, if you just remember that HPQI is a black box composition satisfying this property, then you can already get everything we need today about mixed Hodge structure. And this polynomial here in the fact is called a virtual Poincare polynomial. And we just need to know that it's always easy to compute for the configuration spaces because we know the combinatorics of cut and paste. Okay, so let's put together those ideas by illustrating one example. So let X be C with several punctures. Then Kim in 1994 shows that the ordered or unordered configuration space of X satisfies purity of weight Wi equals to 2i. So that means that the left-hand side here, where 2n minus Wi is replaced by 2n minus 2i, that is something we can compute explicitly. And if you expand that, you get this. And if you now compare the left-hand side and right-hand side, we get Arnold's result. We can directly read all the non-zero Betti numbers here. In particular, the second highest order term corresponds to hi, and you can see why it only starts to appear when n is 2. Okay, so now we're going to present the actual result we have proven, which says that for punctured torus, the hi of its configuration spaces is pure of weight Wi with the same pattern as before. And as a result, the left-hand side is equal to something we can compute, and that is the main result before. And this actually can prove something stronger. We, in fact, use this purity statement. We get all mixed Hodge numbers of Conf and X. Right. So in the rest of the talk, we will just focus on the proof of this theorem because we have seen how this theorem implies our first theorem. And the important point here is that original problem doesn't need any complex variety structures, but we choose to endow X with a complex variety structure of an elliptic curve minus 1 point. Then we can use the mixed Hodge theory to get this result. And before diving into the proof, we present further applications. So in our main theorem, we only deal with one punctured elliptic curve, but actually combining with a nice formula of Napolitano, we can get the similar results for R punctured elliptic curves. And the good feature of those results is that they can be compactly summarized by one or two generating functions. So they answer the question of how to read and comprehend the combinatorial formula for these Betti numbers by Drummond, Cole, and Knudsen in the case of genus 1. And in fact, this Napolitano's result can be upgraded to an isomorphism of mixed Hodge structure. And as a result, we get all the mixed Hodge number in this case. And this will be a result I prove, and I promise that preprint will be coming soon. And it basically says how the mixed Hodge number of X minus with curve of one more puncture can be computed from the case of X. Conjecture the analogous version holds even in high dimension. Okay, so let's point out the sketch of the proof of the purity result. First of all, there is a spectral sequence converging to the cohomology of ordered configuration space. And it gives an explicitly described graded commutative algebra called E2xn, equipped with a graded differential map and Sn action. The graded differential means a differential that satisfies the graded Leibniz rule. And punctured torus has a special feature that the cohomology is pure of weight I, just like the projective varieties, even though X itself is not projective. And we remark that this is no longer true for 2 or more punctures. And this feature allows us to read the mixed Hodge structure from something that can be computed from the explicit data. And to determine this data, we need the algebra E2 and also the description of the differential and the Sn action. And finally, we work out the combinatorics and find out a nice set of elements that span this vector space. And by examining those elements, we can prove the purity result. And to elaborate the last point for a little bit, how we read the mixed Hodge structure is from a bigrading to this algebra. And actually, these bigradings all come from spectral sequence, because the spectral sequence, they all have a form, like each page has E2, PQ, etc. And that PQ is the bigrading. And we know that the PQ bigraded piece contributes to weight P plus 2Q. And of course, also the cohomological degree P plus Q. Okay, so this is how we read the mixed Hodge structure. And we also show that every element is a span of the elements of the form. So there are some explicit monomials. Each element has a norm by degree. So R, S1, S2 here are just 0 or 1. So this means that those elements are either there or not there. Right. And you can check yourself that all these generators live in by degree PQ such that P minus Q equals 0 or 1. You can actually check the 6 choices of this R, S1, S2 tuple. And this will be the key, as we will show next page. The next remark here is that this E3SN data, it has to, this depends on the data of the differential map. And if X were projective, then differential would be too messed up, and we wouldn't get a result as nice as this. So this is the reason why we can do the case where X is not projective. And in fact, there are fundamental difference in terms of the even in a phenomenon from the projective case and the non-projective case. And this table shows how we recover the mysterious WI. So here we list the by degree, and we draw we mark down the weight of each cell given by P plus 2Q. And to read the certain cohomological degrees like H3, we just sum up all the entries in the we're not summing up, we sum up all. So we for each by degree, we imagine that there's a piece there, a piece of that by degree there. So we sum up all the pieces of the by degrees labeled in blue, then we get H3. And the assertion of last page is that P minus Q must be 0 or 1. So all the non-zero pieces are concentrated in the strip here. So if we try to read H3, then we see that these blue things only hit the stripped region once. So this means that H3 only has weight 4 p's. And you can do this for other p's. For example, H5 only have weight 7 p's. And you can see that if you just read the weight number in this strip, you get the pattern WI. So this is the picture, and this finishes the proof of all the main results. And there are some several remarks there. So first of all, for X is punctured torus, the ordered configuration space has no purity, unlike the punctured affine line or the punctured complex plane. So the reason is that we need to take Sn invariance to kill something. And all we need here is just the genus being 1 is a nicer case. We don't need the group structure of elliptic curves. And actually, it can be proven that for high genus or more punctures, there is no purity. The same proof shows a purity for the Galois module of the Etel cohomology, elliptic cohomology. where X is still the one punctured curve, but it's now over a finite field. We wonder if anything can be said about Z coefficients. And the non-results are, they have torsion. So indeed, there must be more care that has to be taken. In further work, I expect that the method works for one punctured smooth projective variety in a way that is nicer than general, because the top cohomology vanishes in this non-projective case while the mixed Hodge structure is still pure. So the next obvious thing to do is higher genus curves, and actually they are there are nicer behavior, except that you don't get the purity, so we don't get the generating function immediately. And again, one can understand the multi-punctured case using the one-punctured case, like if the one-punctured case can be understood, if the following conjecture holds, and this is the so-called high-dimensional analog of what I said before, and now I point out what a high-dimensional analog is. The degree shift here all depends on the dimension of the non-projective variety. And we point out that when X is projective, then it is known to be false. So the non-projectivity is important. Okay, so final summary. We find a coherent way to understand all the Betti numbers, and also for multi-punctured torus, just given a one-punctured case. We explain the mysterious ways Wi that appear. The cut and paste of configuration spaces are well known, but we need to use mixed Hodge structure to harvest it. The story of non-projective varieties is not very different from the projective case. And actually, there are works done about projective curves. And also the mixed Hodge numbers are computed. For more detail, please refer to the preprint. Thank you.